Welcome back. This is the second video on the hyperbola. We're looking at it from a theory point of view, and there'll be others, of course, where we do it from a numerical point of view, which hopefully I think this will clear up some of the theory. One of the things I would like to make clear from the get-go is that there are two styles or types of hyperbola. There's a type 1, which we discussed last time, is right here, where the transverse axis is horizontal and the parts of the curve, I think they're called branches, is the technical name in most books, cross the x-axis. In this case, notice that the a squared is connected with the x squared. In other words, the a squared goes with the positive. All right, type 2, you still have the transverse axis, but this time it's vertical. And this would be 0 comma a, this would be 0 comma negative a. And so we're still dealing with that in the same sense. Notice that in this case, the a squared goes with the y squared. But again, the a squared for a hyperbola goes with the positive term. Okay, that's how we finished up last time. So this is the second theory on the hyperbola, and a couple things we have to get clear. All right, first thing, in a hyperbola, c is greater than a, and you should be able to tell that by simply looking at the diagram and plotting out a, which is a vertex, and c, which is a focus or a foci. Yeah, focus, singular. And from the derivation, we express c squared minus a squared, and we represent it by b squared. So when you put this around, you get what looks like the Pythagorean theorem. Now, this is similar, but not the same as the relationship in the ellipse, in the derivation of the ellipse. Here, with a hyperbola, since c is greater than a, the c squared term goes by itself, and it looks like Pythagorean theorem, whereas with an ellipse, a is greater than c because the focus is inside of the ellipse. So therefore, you had a squared was by itself. A squared equals b squared plus c squared. So you have to watch out for that a little bit. It can be a little tricky. Okay, next item with an hyperbola, and also true of an ellipse, but for different reasons. With a hyperbola, the length of the latus rectum is also 2b squared over a. So this is to demonstrate why that's true. Okay, so here we go. And I'm going to do the situation where we're looking at a horizontal transverse axis. In other words, the x squared term is the positive term. And it says here, suppose a focus has coordinates c comma 0, here we are, okay, and one endpoint on the latus rectum. Okay, one endpoint lattice rectum would have coordinates c comma y, and because of symmetry, we're going to assume this is centered at the origin. We'll move them around in the examples later on. The other endpoint of the lattice rectum would be c comma negative y. Okay, by symmetry, this length is y, and this length in absolute value, because length is positive, right? This length and this length are each y, therefore this is 2y. Okay, so we're going to begin with the standard form of this type of hyperbola, and we're going to substitute in x equals c, because at x equals c, the latus rectum touches the hyperbola. Okay? And we're going to find, if I substitute in, you get c squared over a squared minus y squared over b squared is 1. And we're going to go through the same type of derivation that we went through with an ellipse. We're going to solve for y squared. All right, so we're going to multiply everything by a squared b squared. So we end up with b squared c squared minus a squared y squared equals a squared b squared. And we're going to solve for this term, because that has the y squared. So we're going to move this over to the right, making it positive. And this term, which doesn't have a y or y squared, it's going to the left, it'll become negative. So we're going to get b squared c squared minus a squared b squared, and we'll be dividing by a squared. So this is the value of y squared. Okay, we then factor out the b squared from the top, okay? And in place of this, we're going to remind you that we used b squared, right? That's what we talked about up here. Okay, so b squared is c squared minus a squared. Same substitution we made before. So this is b squared, and this is b squared. So you multiply it out, b to the fourth over a squared. You take a square root, and of course you get b squared over a. We're taking a positive value now, but that's why, double it, you get your 2b squared over a, which is the what we use to measure the length of the lattice rectum. And just like with an ellipse, it's going to be really good to help us graph this thing to know how squished, how stretched out the top and bottom part of the branch is. Okay? All right. A little bit of a summary here. Based on the relative values of A and C and these relationships, this is a chart that might be worth understanding. Eccentricity is C over A. Circle, eccentricity is 0. Parabola, I mentioned this a few times, eccentricity is 1. With an ellipse, since C is less than A, you get a fraction here which is less than 1. So the eccentricity, or squishiness of an ellipse is between 0 and 1. With a hyperbola, you got just the opposite type of situation, and C is greater than A, and that's why eccentricity for hyperbola is greater than 1. Okay, so those are some of the issues I wanted to cover, and I also want to cover why the hyperbola has these asymptotes in the form of plus or minus b over ax. That's important. Now, it's worth noting, and this is on Blackboard. I believe I put this up there. All right, it's worth noting that we're taking the example of the type 1 hyperbola, okay? The other type, you're going to have a over b times x because of the orientation. It's now flipped, okay? But at any rate, I'm doing this one, and I'm going to demonstrate why that's true. And it's a little bit of algebra here, and it's almost calculus, all right? So this will be something you'll see in calculus a little later on if you take Calc 1. In fact, you should see this in Calc 1. Okay, so we're looking at the standard type 1 centered at the origin, and we want to show why the asymptotes, those are the lines that the branches approach as we go out. Positively, x approaches positive infinity, or negatively, as x approaches negative infinity. Right? We're going to show why that is. Okay? And this is important because it's going to help us draw the asymptotes later. It'll give us their equations, and it's all based on this fundamental rectangle. Okay? So, just to repeat, this is a type 1. Therefore, this length is 2a. And this length, the length of the conjugate axis, is 2b. Okay, so beginning with the standard form of type 1 hyperbola, we've talked about that, we're going to first solve this for y. What that means is we're going to move some things around. Okay, so here's what I did. I moved this over here to make it positive and a 1 over here to make it negative. You get that. And I multiplied everything by b squared to get that. Let me shrink it down a bit so we can still see the diagram. All right, so this is y squared. Now, the idea is, let me put it back up. The idea is we know from experience we want to solve for y. Also, notice this is the form y equals. So part of our goal is to solve for y. So I want to anticipate that in order to do that, I'm going to do a square root. So anything that has squares in it, I sort of want to pull that on the outside. So this is going to be a little bit unusual because of the razzle-dazzle that occurs here, but watch what happens. Continuing, we factor out x squared over a squared in anticipation of taking square roots of both sides. So this is going to come out, and it's going to make this term here a 1. And this term is going to magically become a squared over x squared. Now, let's check what we just did. This is what I factored out. Okay, and again, because I want to do a square root. Okay, so if I multiply back x squared over a squared times each of these terms, if I did it right, I should get what's in here. So let's check. X squared over a squared times 1 is x squared over a squared. Great. And this times, it's reciprocal, right? You got is a 1, so this works out perfectly. Then what I do is I'm going to take the square root of both sides, and we know I'm going to get a plus or minus here. Okay, this time it matters. And bx over a, all right? And on the inside, over here rather, I just get the square root. Now, here's the idea. This 1 is a constant, a is a constant, so a squared is a constant. So this fraction has a constant numerator, constant top, and the bottom, as x gets very big, meaning moving to the right, or as x gets very small, moving to the left, x approaches negative infinity. And this little arrow here means approaches. It's doing a limit without using the limit word. Okay, so we have a fraction, and the top is constant, and the bottom is getting bigger. So you just understand that when the bottom of a fraction gets bigger and bigger and the top stays the same, it's going to approach 0. So we find that this fraction approaches 0. Okay? Now, if the fraction is approaching 0, then 1 minus 0, what's under here is approaching a 1, and you take the square root of something that's really close to 1, you'll get close to 1. All right, so this means approaches. So it follows that as x gets bigger and bigger, this thing approaches 1. 1 times this is that. So you get y equals plus or minus b over a times x. And I want to repeat, that's for a type 1 hyperbola. If you're doing a type 2, this is going to be a over b, because now the vertical axis is vertical. It's flipped. Okay? Now again, let's look at our picture. This is 2a, this is 2b. In particular, this is a, and this is b. So b over a is simply changing y over changing x. It's the slope. So that's why that works. And if you take a look at the type 2 type of situation, same type of thing is going on. That's why it's going to be plus or minus a over b times x. All right? And we're going to look at that in some subsequent videos where we just do numeric examples. This has been theory. Okay? So I hope the explanation was reasonable, and you're going to probably have to go through this again. Again, you can stop the video, or pause it, go have a lunch snack and come back, take notes on it. But this is on Blackboard. I recommend you print it out. Okay, so until we meet again, let me stop the recording.